All right, so here's a for instance. On Mars, at a much lower atmospheric pressure than we have, the freezing point actually doesn't change very much. The boiling point does, but the freezing point doesn't. So we're still talking about 273 Kelvin. So what I want you to figure out is, now one of the water-soluble compounds thought to be present on Mars is magnesium chlorate. And I see another error there. Come back here. This is actually MgClO4 too. Now, what concentration of this would be necessary to reduce the freezing point to about 220 Kelvin, which is the average surface temperature of Mars? So the idea is that we want to reduce the freezing point such that it's liquid, at the average surface temperature of Mars, not always frozen. So these constants, turns out you have to look those up, and I will tell you that this is 1.86 Kelvin kilogram per mole. And the other thing to know is that those are solvent properties. So these constants apply to solvents, and you look them up. So let's talk about, what concentration of the magnesium chlorate you would need to actually do this. So hit pause, think about it for a bit. All right. So we're going to rearrange this expression and solve for temperature, or the change for the concentration, sorry. And our change in temperature is kind of the way you think about it is, we want the initial freezing point for the pure water is 273.15. We want to get it down to 220.15 Kelvin. We have an I factor of 3 for this because we get 1 magnesium, 2 chlorates, 1.86 kilograms kelvins per mole. So let's do the dimensional analysis. So the kelvins are going to cancel, and we get inverse kilograms per mole, which means we have moles per kilogram. That's the units of molality. So we would need 9.5 molal magnesium perchlorate to keep the water on Mars from freezing on an average day. And I will tell you that is a particularly high concentration, or it's a very high concentration. Now, one of the interesting uses of this freezing point depression is back in the old days, and sometimes still now, this is actually a way to determine the molar mass of the solute. So recall from the definition, molality is defined as the moles of solute divided by the mass of the solvent in kilograms. So if you rearrange this, you can equate the moles of solute, so not rearrange. Now the moles of solute is equal to the mass of the solute. Now this is what you actually weigh out, divided by its molar mass. And here, double capital M I'm using as an abbreviation for molar mass here. So let's substitute this expression for the moles of solute into this molality equation right here. And you get that the molality can be expressed as the mass of the solute divided by its molar mass divided by the mass of the solvent. Now, with this expression for molality, we can express the change in the freezing point, which is normally the Van Hoff factor, the freezing point constant, and molality. Now, putting this expression into molality, we get the change in the freezing point temperature is equal to the Van Hoff factor times the constant Kf times the mass of the solute divided by the molar mass of the solute divided by the mass of the solvent. And in most cases, you can determine all of these independently except for the molar mass of the solute. You measure this, you know this, you can take a stab at that, and you look up the freezing point constant and you know how much solvent you put in. So if you rearrange all of these to solve for the molar mass of the solute, you get this. The molar mass of the solute is equal to the Van Hoff factor Kf times the mass of the solute divided by the freezing point temperature change and the solvent mass. And I will note that this is normally done with covalent or non-ionic solutes for whom this Van Hoff factor is going to be 1. And so you can determine the molar mass of the solute by adding a known mass of the solute to a known mass of solvent, and then just simply measuring the change in the freezing point. So using that relationship, work through this one. Alright, so pure benzene freezes at 5.5 degrees Celsius. You added 4 grams of an unknown but non-ionic solute, so I is equal to 1. And the freezing point goes down to 2.31 degrees Celsius. And for benzene, Kf is 5.12 degrees Celsius per kilogram per mole. So hit pause, turn this one out. All right, from the previous slide, rearrange for the molar mass. And when you punch in, so again, the Van Hoff factor I is assumed to be 1. Kf, we put in 4 grams. The freezing point change was 5.15 minus 2.31, 55 grams of the benzene. That gives us a molar mass of 0.017 kilograms per mole. So be careful of your units here. This usually comes out in kilograms per mole, which is normally not what you see, and that translates to about 170 grams per mole. So this was a common technique used for non-ionic compounds that have a molar mass of usually over a couple hundred grams per mole. And finally, the math for the boiling point elevation looks exactly the same, but it's different. So we still have the Van Hoff factor I, which is still calculated the same way and is still incorrect in this slide for calcium chloride, so I have to fix that. So in this case, it is 3. The other things to be aware of, the constant for the freezing point is different. So this is Kb, not Kf, and this is called the ebullioscopic constant, which is just really fun to say. And again, this is a property of the solvent in the system. Little m, as always, is the solute concentration. I is the Van Hoff factor, but it's the same thing. And the important thing is that this scales linearly with the concentration. So if you double the amount of solute, you will double the amount by which the freezing point was changed, and so on and so forth. And so these are cryoscopic properties, and we're going to apply this to candle making in lab. See you then.